Alright, welcome back. We are looking at section 4.3 on linearly independent sets and bases. So, we have an index set of two or more vectors with our first vector is not the zero vector, is linearly dependent if and only if there is some vector j that is a linear combination of some of the preceding vectors. So, like if you have v1 is like 1, 0, v2 is like 2, 0. These are not linearly independent, they are linearly dependent because v2 is 2 times, these need hats. v2 is 2 times v1. Right, so then it's a linear combination where it's just one vector, but you can represent some next vector by a linear combination of preceding vectors. So this is a linearly dependent set of vectors. So we can also think of about this kind of like with polynomials. So if we have p1 of t is going to be 1, and then p2 of t is t, and p3 of t is 4 minus t, then we have a linearly dependent set in our polynomial space, because p3 is just, this is p1, I guess scaled up by 4, and then minus just our p2, which I guess we have right there. So, this is linearly dependent. If we had sine and cosine of t as our set, that is linearly independent. And if you think about that, like positively even think about why sine of t and cosine of t is going to be linearly independent. You think like circles. The sine of t and cosine of t are not going to be multiples of one another as vectors in our space. So there's no scalar that you can just multiply cosine of t to get sine of t, or multiply a sine of t to get a cosine of t for any t's that we plug in. But if you think about that, it's not just like trig is going to be our panacea, it's going to fix everything in terms of linearly independence, because, you know, if you have sine of t times cosine of t and sine of 2t, well, double angle sine of t plus t is what? Sine, cosine, cosine, sine, so doubling that. So we got our scalar, oh, there it is. Yeah, we got our scalar that gives us linearly dependent relationship. So, why are we talking about linearly dependent things? Well, for a basis, we need the minimum amount of information in order to have to completely get to everything in our space. So if we have H as a subspace of our vector space V, and we have an index set of vectors B1 to Bp, then that's going to be called a basis. This set of vectors is going to be called a basis as long as it's linearly independent. So each of these is giving us new information, a new direction that we can go. And the subspace that we're spanning by our set of vectors is exactly the subspace H. So, because we could have a linearly independent set of vectors, but it doesn't span our subspace, and so then that doesn't count as a basis. Because even if you think about okay, so we got our elementary vectors, we got 1, 0, and 0, 1. If we have that, but then we're looking at this 1, 0, 0 and 0, 1, 0. Well, those two are linearly independent, but those don't span R3. So that would not form a basis for R3. Okay. So I alluded a little bit to this vocabulary before, but if we have E sub 1 to E sub n are columns of our n by n identity matrix, then we're going to call them the standard basis for Rn. And so standard basis because we're just taking columns from our identity matrix. It's beautiful. And there's a nice picture there. Alright, so your task is to consider these three vectors and determine if they are a basis for R3. So pause the video, try it out, try to figure out how you could possibly determine if these are going to be linearly independent or not, and if they span R3. There's any way that you could do this, but what I'm really feeling is just putting those into matrix and seeing if we RF it, what happens if we get enough pivots, and we do so. Because of our invertible matrix theorem, we know that yes, this is fantastic. Our invertible matrix theorem, yes indeed. Alright, solid. Let's look at the next one. So we have a bunch of polynomials, and how are we going to verify that that is a basis for like our polynomial space? This is called the standard basis for a polynomial space. So how would we verify that this is indeed our basis, our standard basis for P sub n? Well, in order to figure out if something is linearly independent, one way is to see if it only has a trivial solution. To see if we just multiply each of these by zeros, by our scalar zeros, if that's the only way for us to get our zero vector out as our solution. And I think so. I think that's true, right? If we just have like 0 times 1 plus 0 times t plus 0 times t squared plus ... plus 0 times tn, that's going to give us our zero vector. And that's the only way. And well, the fundamental theorem of algebra says that the only polynomial that gives us like we have as many zeros as we have for our degree of our polynomial, and the only like contradiction to that is the zero polynomial. So this only works if we have zeros as what we're scaling, and so we have linearly independent ones. We have three vectors, and H is going to be the span of these vectors. We're noticing that V3 is a linear combination of our preceding vectors, so they're not linearly independent. And so how can we show that our span is the same, and how can we find a basis for our subspace? So pause the video, think about it, and geometrically also think about what we're getting here. So we know that every vector in our span of V1 and V2 is going to be an H, because we can just say that we have some constant 1 times V1 plus constant 2 times V2 plus, and that's going to equal some constant 1 times V1 plus constant 2 times V2 plus 0 times V3. So that's nice. And we also know that V3 is 5V1 plus 3V2. Right? So, if we're looking at something that's in, like, let's just say that x is going to be in our H. Then we can also say that C1, that's going to be a linear combination, C1v1, C2v2, plus C3v3, right? But we also know that this is V3, so maybe we'll change colors so that we get that substitution in here of 5v1 plus 3v2. Oh, sorry, poor spacing. And so, we just do a little algebra, and then we're good to go. We can rearrange this. So we get, this is equal to, what, C1 plus 5C3, that all times V1, and C2 plus 3C3 times V2. And so we know that x is in the span of V1 and V2 because we can write it just as a linear combination of V1 and V2. We do have that our span of V1, V2, V3 is equal to our span of V1, V2. H and our span of V1, V2 is going to be the same set, and that's going to be a plane. It's going to be a plane that looks kind of like this, where we have V3 can be written as a linear combination of 5v1 plus 3v2s. Right, that's what we're showing here with this grid, and that is gonna be our span of V1, V2. Alright, so spanning set theorem. Let S be our set of vectors, V1 to Vp, be a set in V, and H is the span of those vectors. If one of our vectors in S, say V sub k, which is somewhere in there, is a linear combination of the remaining vectors in S, then the set formed from S by removing V sub k still spans H. So that was like our V3 was 5v1 plus 3v2, and so we can just take out V3 and still span our set H. And if H is not equal to our a set of our zero vectors, then some subset of S is a basis for H. So, like we were looking at before, where we had V1 and V2 were a basis for H. There we go, spanning set theorem. So, pause the video, try to figure out, find a basis for the column space of B, where B is equal to this. Well, this first column and this second column, they're linear combination. The non-pivot column, this 4, that's a combination of a pivot column, which is this one, right? 4 times column 1 is going to give us column 2. And our non-pivot column here is going to be 1 times our first pivot column, 2 times our first pivot column, and negative 1 times our third column, which is our second pivot column. And so we have 3 vectors that are useful, and so that is our basis, which curly B is going to be 1 0 0 0, 1 0 0 1 0 0, and 0 0 1 0. So there's our basis for our column space. Elementary row ops on a matrix don't affect the linear dependence relations among the columns. So, if we're doing row reduction, or if we're given that 2 matrices are row equivalent, then there's things that we can say about those in terms of the linear dependence relations not being changed. That's really nice, because if you're told that this matrix A, which has far less zeros than I would like, is row equivalent to our matrix B that we had above, this matrix B, then how are we going to find a basis for the column space of A? pause the video, think about it. Well, since we know that we have our linear dependence relations not affected by our row operations, then since we were using column 1, 3, and 5 before, nothing is stopping us from using column 1, 3, and 5 now. So we can take our columns, our vectors A1, A3, I can't write 3, A3, and A5, and there we go. That is our basis for our column space of A. One more thing is that those pivot columns of a matrix A form a basis for column A. That's what we saw up here, where we had our pivot columns from our reduced form. Those told us what our basis was. So there we go. So pause the video and work on this problem. Let V1 be 1, negative 2, 3, and V2 be negative 2, 7, negative 9. Determine if V1, V2 is a basis for R3. Is V1, V2 a basis for R2? So pause the video. It's a yes or no. So do V1, V2, do those get us a basis for R3? Well, we can do some row ops. We can like make an augmented matrix and think about it, where we get what, 1, negative 2, 0, 3, and then 3, 0, negative. Oh, but this will go away, right, because of this one. Okay, so we don't have enough pivots, so we don't have a pivot in each row, so no, not a basis for R3. And is V1, V2 a basis for R2? No, because it's not in R2, right? So, like, we could think about maybe the projection, but that's not, but V1, V2 is not going to give us a basis for R2. Alright, and let's think about this problem. So let's let our vectors V1 and V2 stay the same, and then we add some V3 and V4, find a basis for the subspace W spanned by V1, V2, V3. So, pause the video, try it out. Find a basis. Our basis, we need to do some RFing and pull our pivot columns. So let's do that. So we got 1, negative 3, 4. Oh, that's different. Sorry, I totally lied. These vectors are different. Okay, we have 6 from what we had before. Negative 2, 2, negative 2, 3, negative 4, negative 8, 9. Okay, and then we'll do some row reduction, and what do we end up with? We got 0, oh, nope. We got 1, 6, 2, negative 4, 0, 20, 4, negative 20, and 0, negative 25, negative 5, 25. Curious. These look remarkably similar, right? So we'll zero out this last row. And I guess we can reduce these by 4. So we have what, 5, 1, negative 5. Alright, what are our pivot columns? Our pivot columns are the first two, right? Our first two columns, and those will form a basis for our for the column space of A, which is this matrix that we made, and that's going to give us a basis for W. So our basis for W is going to be 1, 0, 0, 6, 5, 0. Boom. Alright. And we didn't have to totally RF it. We could just reduce until we found our pivots. Okay. Last thing. So we have V1 and V2 are our first two columns of our identity matrix, of our 3 by 3 identity matrix. And S is going to be, or H is going to be the set of all SS zeros, where S is your real numbers. So that's going to be a line. then every vector in H is a linear combination of v1 and v2 because we can write this as a linear combination. Now, is v1, v2 a basis for H? Well, v1 and v2 aren't in H. v1 is not a set in the set of H, and v2 is also not in the set of H, so they can't form your basis because v1 and v2 are going to give you the like this plane, where this one I guess is 0, 1, 0, 0. This direction is 0, 1, 0, and then up here is 0, 0, 1. So our plane, our like kind of flat plane for x1, x2, this one's x1 direction, x2 direction, x3 direction. That's going to be our span of v1, v2, and H is only a line here. I guess I should change colors. A line here, going through all of that and going like backwards. So, no. Alright, so what did we do? We talked about basis and how it's great to use linearly independent set of vectors in order to form a basis for a space. And we had our spanning set theorem, where we have, if you have a one vector that is a linear combination of other vectors in your set, then you just take it out. It's totally cool. It doesn't change what you span. And that is about it. All right. Bye.